some of the rules are not being obeyed by this particular quantity, and that is why it is termed as a scalar quantity. A pressure applied at any point of a fluid is transmitted undiminished and equally in all directions. You're applying a pressure onto that particular fluid so that that particular small pressure is amplified and helps you stop your bike. Hey all, I'm Hari Krishnan from the Department of Physics, Vidhyaashram PU College, the Temple of Excellence. And we are going to see a new chapter here today, that is the mechanical properties of fluids. In the previous class, we learned about the mechanical properties of solids, and now we are going to see what are the mechanical properties of fluids. What are the specialities, properties and nature of these particular fluids, and what are fluids exactly. So let's get on to it. So the first thing when we talk about a fluid is the pressure. So what exactly is pressure? We do know that pressure is nothing but force exerted per unit area, or simply force by area is nothing but pressure. So to put it to perspective, if I have a needle, or let's say if I have anything with a sharp tip, and if I try to pin it onto my hand, I will feel the pressure on my hand. That is because even though I am applying a force, let's say of F, down this particular nail onto my hand, this particular force is being exerted on a very small particular area. Hence, I'll be experiencing more pressure. So just to put it into perspectives, pressure is nothing but force that is applied per unit area. So again, why are we talking about pressure? That is because I just told you that fluids are not just liquids but also the gaseous matter that is surrounding us, which means our entire atmosphere is surrounded by a fluid, right? Our oceans are actually filled with fluids, that is liquid state, and our entire atmosphere is also filled with a fluid that is in gaseous states, by generally many types of gases including argon, helium, oxygen, xenon, many other gases are there in trace quantities also. But mainly the thing is that fluids are a combination of gases and liquids, which means if there is molecules spreading all around us, then these molecules will exert a pressure onto us also. Imagine if I keep anything inside a beaker full of water, then you know that that particular beaker full of water will be exerting pressure onto whatever it is kept inside that particular container, right? So in order to have a definite idea, let's say this is deep sea. This is deep sea. So let's say about 10 kilometers, let's say 10 kilometers into this deep sea, there is a submarine. Okay, there is a submarine like this. There is a submarine like this. So if there is a submarine like this inside the deep ocean, if there is even a small crack, the entire ship, the entire submarine will be crushed, right? That is because as you go down, the pressure will automatically increase, right? It is not just for the sea I'm talking about. This is actually true for any fluid. That is, even if we go down the sea, and even if we go up the mountains, the pressure actually increases or decreases. Or simply to put it, the pressure actually affects us. You might have learned in your previous classes that as we go up, the pressure actually decreases. As we go down, the pressure actually increases, right? So pressure is actually a fundamental factor that influences anything that is concerned with fluids. So that is why we are starting with pressure. And the definition of pressure is nothing but the force that is exerted per unit area. That is one. So pressure is the force that is exerted per unit area, and the SI unit of pressure, the SI unit is nothing but force Newton area meter square. So you can say that, okay, it is Newton per meter square, or you can also call it as pascals. Generally, we call it in terms of pascals. Or if it is the atmospheric pressure we are measuring, we measure it in terms of ATM, 1 atmospheric pressure, or in terms of Pascal, how many Pascals it is. So Pascal is actually a unit that is used to measure pressure. So Pascal is actually a scientist who studied a lot and contributed a lot in the field of physics. So that is why we call this as Pascals, or simply you can also use the unit that is Newton per meter square. Now the general thing is that, okay, is this a scalar or a vector quantity? Is this a scalar or a vector quantity? It is actually a scalar quantity. But sir, there is a force here. If there is force present, it should be a vector quantity, right? Not exactly. We saw that it has to obey all the laws of vector addition and vector principles in order to be a vector quantity. That means that some of the rules are not being obeyed by this particular quantity, and that is why it is termed as a scalar quantity. So what is that particular rule? So again, that is because I told you force exerted in a particular area is known as pressure. So if I take a random example of a beaker which is having some water in it. So let's say this is the beaker that is containing the water. And if I randomly pick one molecule, one water molecule at the bulk, then I can say that, okay, there is a force being exerted onto this side, this side, this side, and this side. So in the bulk, the molecule is not actually experiencing force in a particular direction. Or to put it more clearly, we can say that this particular molecule that is in the bulk is not experiencing a force in a particular specific direction. So we cannot specify a specific direction. Hence, we cannot say that, okay, there is a specific direction for pressure to be applied. So that is why we generally say that, okay, pressure is a scalar quantity and it is found through the equation force divided by area. So what is the next thing? The next thing is that, again, we are going to start from the unit, the man who contributed that particular unit, that is Pascal. So we are going to learn about Pascal's law. Again, this particular chapter, that is mechanical properties of fluids, is a very big chapter and it has a lot of important questions, which means you have to pay attention and you have to study and understand all the principles in this particular chapter. So starting with Pascal's law. So what Pascal's law tells us is that if I apply a pressure onto a fluid, or if I apply a force onto a fluid at a particular location, then that particular force will be transmitted throughout the liquid without any diminishing nature in that particular force applied. Or much more specifically, we can say that a pressure applied at any point of a fluid is transmitted undiminished and equally in all directions, which means that if I have a tube like this, and let's say it is filled with water or any type of fluid, and if I apply a pressure onto this particular region, then what happens is that how much ever pressure I'm applying onto this particular region, the same amount of pressure is experienced here also. That is, if I applied 10 units of pressure here, that very same 10 units will be transmitted across this fluid to the other end. There will be no loss in that particular pressure which I applied here. How much ever pressure I'm applying here will be transmitted the same manner to the other end. So that is known as Pascal's law. Now, why exactly is this law particularly very important? Why is that Pascal's law? Just a simple logic. That is, if I apply a pressure onto one end, the same amount of pressure without any loss is experienced at another end if the medium is a fluid. So why is it so important? It is so important because many of the applications we have here today in this particular daily life we live in is because of this particular law. For example, if you have seen JCBs digging sand, or a lift which is going up, some buses which are lifting up, or even platforms which race, all of that is because of Pascal's law. Or simply to put it, we are using Pascal's law in order to achieve different phenomena, different feats using Pascal's law. That is hydraulic lift, the braking system in your cars, the braking system in your bikes. You might have seen that there is a small, if you have seen bikes, there will be a small box like this just above the brake lever. This is where the brake fluid is actually stored. And from there will be a small wire which is connected to the disc or the drum brake in your bikes. So when you squeeze the lever, what you're doing is that you're applying a pressure onto that particular fluid so that that particular small pressure is amplified and helps you stop your bike. So how exactly that happens, we'll study. Not exactly the brake, but how exactly that particular dispersion of pressure happens, that we'll study. But the essence, the inherent law behind it is actually Pascal's law. It's not just for brakes. You can also use it for hydraulic lift or power cables or forklifts or even JCBs, which operate heavy machineries using just simple hydraulic mechanisms. So again, this is the applicational principle of Pascal's law. So this is an application of Pascal's law, simply known as hydraulic lift. So this particular derivation is actually very important. It's very short, but it's very important. And it shows us the importance of Pascal's law. So how exactly does this particular equipment work, or the hydraulic lift, how does it work? You might have seen that when somebody wants to do a car wash or somebody wants to inspect what is under a car or something, they just simply drive onto a platform and somebody pushes a lever and suddenly the entire platform raises up. So how does this hydraulic lifting happens? So that is what is actually known as a hydraulic lift. So how exactly does that particular effect occur, or how is it exactly the application of Pascal's law? So let's see that. So first I have an equipment here which is nothing but the hydraulic lift. So here I have two pistons. This is piston number 1 and this is piston number 2. And in the piston number 2, I have placed a load. Let it be a car, a bike, or any load you want. Okay, it is placed there. So the difference in this particular picture is that here the first piston, which exerts, let's say, a force of F1, it is exerting a force of F1 and it is only having an area of, let's say, A or A1. In this particular figure, on the left hand side, this particular piston, which is going to exert a force of F1 when it is compressed, is only having an area of A1. And similarly, if you look at the other side, we can say that, okay, compared to this area is much more larger. So let's say that, okay, that particular area is A2, and let's say the force that is being, or that is going to be exerted onto that particular piston, it is going to be F2. Okay. And this entire chamber is filled with some kind of fluid. Okay, this entire chamber, let's say this entire chamber is going to be filled with some kind of fluid. It is completely filled with fluid. There is no gap. So what happens when I push this particular piston? The entire fluid is forced out through the other end. Or simply, if I apply a force of F1, another force of F2 is experienced at the other end. That is what is lifting this particular load up. So how can you represent this mathematically? And what is the significance of this size change? So again, since this is the application of Pascal's law, we'll start from the equation that is for pressure. So we know that pressure is nothing but, force divided by area. Or simply it is F by A, right? In this particular case, we can say that, okay, there is one type of pressure exerted here and another type of pressure exerted here, because they're going to be different in magnitude, because the area is different and the forces exerted will also be different. So if I say that, okay, this is the first force exerted and it is the area A1 in that particular case, or in that particular specific location, then the pressure experienced will be P1. Okay, and similarly on the other end, I can say that, okay, the force experienced is F2 and the area of that particular region is A2, hence the pressure experienced there will be P2, right? So there will be pressure P1 here and pressure P2 there. So let's name it as equation number 1 and this as equation number 2. But sir, what is so special about this? Okay, we know that there is going to be a pressure here, there is going to be a pressure here. What is so important or what is so significant about that particular revelation? So the significance is that Pascal already told us a law which stated that if I apply a pressure onto a fluid, then the same amount of pressure is going to be exerted at the other end, which means no loss is there. There is no diminishing value. When I apply a pressure here, same pressure should be exerted at the other end, which means that I can say from Pascal's law, I can say that 1 is equal to 2. That is, P1 is equal to P2, or simply F1 by A1 is equal to F2 by A2. That is it. It's a simple derivation. See, it's a simple derivation. This is the equation that helps us achieve hydraulic lift. And how it is actually achieved, it's again very simple. That is because if I write F2 here, just an equation in terms of F2, I can say that, okay, I'll bring A2 here, which means F1 A2 divided by A1 will actually give you F2. So let's say hypothetically, what does this actually mean? Hypothetically, let's assume that F1 is a small force which I am applying onto the small area. Let's say the force I'm applying is 10 newtons. I'm applying a force of 10 newtons. And let's say the area here is 1 meter square. So the area here is 1 meter square. So I'm applying a force of 10 newtons onto this particular region, that is 1 meter square, which is in area. So which means that F1 is nothing but 10 newtons and A1 is nothing but 1 meter square. And A2, let's say it is a comparatively larger area. Let's give it 2 or 2 meter square. 2 meter square is the area, that is A2, just twice as large. It is much more larger, but let's say for argument's sake, it is only double. So 2 meter squares. Then what will happen to the net force that is applied on the other end? That is, F2 will now be equal to 10 times 2 divided by 1. Right, it is 20. 20 newtons is the force that is experienced at the other end, which means that the force I applied here at the narrow end is actually doubled at the other end. If I simply push like this on this particular end, the other end is actually giving out a punch. That much change in force has occurred just because this particular fluid is in between. This particular property of a fluid is because of its nature itself. That is, compared to gases, fluids and solids are nearly incompressible. So that is why this particular law actually exists. Fluids and solids are practically almost incompressible. They don't change their volume really drastically. That is why we can apply this particular law. And yes, this particular law is an application of Pascal's law. So you have to remember how to derive this particular derivation. And one last thing is that this particular equation, there is A2 divided by A1. This has not been asked, but it is good that you know this also. So what it states is that A2 by A1 is known as mechanical advantage, because this ratio between these two areas is what provides that increase in that particular force experienced, right? Whatever force I'm applying here, it is doubled right now. So A2 by A1, that particular ratio is what playing or giving us a mechanical advantage. So that particular ratio is known as mechanical advantage ratio. And simply we can also say that F2 is greater than F1, right? The force that is applied on this particular end will be greater when it is compared to the force which is experienced in the first area. So that is all about hydraulic lift. So the next topic is fairly simple. It is nothing but variation of pressure with depth. We already know this. We already know this in our practical lives also. That is, when we go down in any type of fluid, the pressure actually increases. That is fairly simple. So let's assume that this is a beaker and I'm going to fill it with water. Okay, I'm going to fill this particular beaker with water so that this particular object which is placed inside this is completely immersed. Okay, now this particular object which is kept inside this particular beaker is completely immersed. Now, if I take 2 points, that is the top point, which is, let's call it as point number 1, and the bottom point, which is point number 2, will these 2 points be experiencing same amount of pressure? If not, what are the factors that is going to affect this particular points? So, the point number 1 and point number 2 is separated by a distance of h. That is simply the height of the object. So, if that particular object is having a height of h, point 1 will be experiencing a pressure of P1 and point 2 will be experiencing a pressure of P2. So, why is there a difference in pressure? Obviously, if you think it, if you want to think it logically, or if you want to understand it much more clearly so that you can understand the concept, you can imagine it as such. That is, here point 1 can only or does only have to bear the weight of this much water, right? Only have to bear the weight of this much water. Only that much pressure is being exerted on that particular region. But as we come down, the entire volume up to this stage is being pressed onto this particular point, that is point 2. The more weight of the water is being supported by the second point, right? So this particular region, which is completely immersed below compared to this particular first point, is going to experience more pressure. So what are the factors that is influencing this particular pressure variation? If I say that, okay, if I want an equation in order to find what is the pressure that is experienced at point P2, then I can say that this will be equal to P1 plus H rho G. This will give the pressure at point 2. Or simply you can also rewrite this equation as P is equal to P atmospheric plus H rho G. So this form is also possible. That is assuming that this particular cylinder is very close and whatever pressure is experienced in the second part, on the bottom part, is given by this particular equation. So what is that particular equation? What is H rho G? Obviously H is nothing but the height of that particular object. Now what is rho and what is G? Rho, again you know that rho is nothing but the density of that particular liquid. The density of that particular liquid is given by rho, and G is nothing but acceleration due to gravity, that is 9.81 meter per second square. So again, it is very simple. If you want to know what is the pressure that is experienced at point 2, you can use this particular equation which tells us, okay, it is going to be equal to P1, pressure at point 1, plus H rho G, whatever pressure it is already being experienced here, plus whatever height the object has, times the density of the liquid it is immersed in. You can also say that if it is mercury or oil or any other liquid compared to water, they can be either more denser or less denser than water. Which means if I immerse any object onto that or into that particular liquid or fluid, there will be a difference in the pressure that is experienced by any object. So that is why we take rho. Rho is nothing but density of that particular liquid, or simply mass by volume. Mass by volume is the density. So mass by volume, or simply density of that particular liquid, times the acceleration due to gravity. If it is in earth, we can always take it as 9.81 or simply round it up to 10. There is no problem. But what if the fluid is in some other planet or some other satellite or something, or even in space? Then we have to calculate G also in order to find out what is the pressure that is going to be experienced. So generally our surroundings, that is, we are also immersed in a fluid, right? We are immersed in gases around us. So the atmospheric pressure, we always measure it as almost up to 1 atm. So we just call the atmospheric pressure as 1 atm. It is actually 1.00 something 1, but again we call it as 1 atmospheric pressure. Then again, if any other fluid is present or we want to measure that particular pressure difference compared to atmospheric pressure, we use this particular equation. That is, if you have a car tire, let's say if you have a car tire and you want to measure in the petrol pumps and all that, you might have seen that they measure, they just connect one equipment to the tire and measure how much pressure inside the tire there is. Generally for bikes or cars, it is generally around 35 to 36 atms of pressure. So what is this 35 to 36 atms? So they are just comparing, or they are just measuring compared to the atmospheric pressure, how much more pressure is contained in that particular tire. So this particular measurement is known as gauge pressure. So this particular pressure is known as gauge pressure. Gauge pressure just means that we are comparing how much more pressure is present compared to the atmospheric pressure. Generally it is 1. So compared to the atmospheric pressure 1, how much more pressure is inside this particular tire. So we're just comparing and saying that, okay, this much more pressure is inside this particular tire or inside this particular material. So these kind of measurements is known as gauge pressure, or how much more pressure is there compared to the atmospheric pressure. So what makes all these measurements and all these factors very interesting is actually a paradox. So it is also known as hydrostatic paradox. Hydrostatic paradox. So what is this hydrostatic paradox? Hydrostatic paradox just means that there is a paradoxical nature to this particular liquid. Let's say, let's take water for example. If I have water and let's say that, okay, I am filling water in 3 containers. I am filling water in 3 containers having 3 different shapes. And I'm going to fill each of these containers up to the brim with a liquid, let's say water. I'm going to fill this entire container which is having different shapes. One is an inverted cone, one is like a narrow flask, and one is a broader flask. So I'm going to fill this with water and see what happens. So the only similarity between them is that, okay, their height is similar. The density of the water inside each of this material is also same, right? So if these conditions are actually met, the paradox is that despite them having different types of shapes, that is, earlier I showed you an example of a beaker in which something is immersed in, right? So despite of them having different amount of water in them, that is, different shapes in them, the pressure that is exerted at a particular height remains same. What it means is that, you know that this is completely filled with water, right? So this is completely filled with the same amount of liquid. So this is all completely filled with the same amount of liquid. Now, if I measure the pressure here, let's say at height h, if I measure the pressure here, the pressure P1, P2, P3, that is, this be P1, P2 and P3. All these pressures, anywhere along this line, if I measure the pressure, all will be equal to each other. That is, P1 will be equal to P2 will be equal to P3. Despite having different kinds of shapes, different kinds of volumes, they all seem to have the same pressure if the height, the density, and the acceleration due to gravity does not change. If these 3 factors are remaining same, then the pressure actually remains to be constant. So this is known as the hydrostatic paradox, or simply to put it into words, we can say that what hydrostatic paradox means is that, so the pressure of a liquid inside a liquid column, this is known as a liquid column which contains liquid, a column which contains liquid. So the pressure inside a liquid column only depends upon the height of that particular column, the density of the liquid that is inside the column, and finally the acceleration due to gravity, that is G. These are the only three factors which influence the pressure of that particular region. It does not depend on the area, it does not depend on the volume, it does not depend on the shape of the column, it only depends upon the height, density and acceleration due to gravity. It's a spooky phenomenon because when you see this, you might imagine that, okay, there is so much water here, which means here the pressure should be more. Or there is so much water here, comparatively there should be higher pressure compared to this one. And you'll be like, okay, there is only this much water here, but then the pressure will be low here. But that is not the case. All of these different types of shapes have the same pressure underneath them. So that is known as hydrostatic paradox. So I hope you have understood everything about fluids. That is a brief introduction that I gave here today. In the coming classes, we'll learn in depth about what fluid mechanics and properties are really all about. So until then, thank you.